So this is section 4.2. Eventually we're going to discuss E. But it's actually going to start out with a discussion of simple and compound interest, or continuously compounded interest. Now, just as a reminder of some things here, some of the things that go into our interest formula. A is the amount that you end up with, your ending balance. Probably more formally, it's the amortized value, which is something that you'll see when you buy a house. You get an amortization schedule. Principal, that's how much money you initially invest. N is how many times per year the interest is compounded, and of course T is just time. So we're going to kind of skip this part because we've already practiced calculating simple interest, that is interest with this formula. Although maybe you want to pause the video and reassure yourself that you can get these numbers. Interest gets rounded. These problems should get automatically rounded to the nearest hundredth. Why the nearest hundredth? The nearest hundredth is pennies. So that's the smallest unit that our money goes down to. So all your answers here should be rounded nearest pennies. But let's take a look at kind of a fictional example, maybe inspired by a little old movie clip from an Eddie Murphy movie called Trading Places. And in this movie, they have a standard bet, $1. So we're going to take our standard bet, our $1, and invest that $1 for 1 year. And in as much as we're talking about fiction, we're going to play a little bit more fiction. We're going to give ourselves 100% interest on that $1. That's pretty cool. So the thing to keep in mind about plugging into our formula up above is that this has to be expressed as a decimal. So what's 100% as a decimal? No, not 0.01, not 0.0. Even? It's just 1. It's exactly 1, right? You move the decimal, you move the percent side, you move the decimal 2 places left. So it's exactly 1. We're going to invest that $1 for 1 year at 100% interest rate. So of all the variables in this formula, the only one that hasn't been turned into a 1 is the N, the number of times a year that interest has been compounded. So essentially we end up with this right here. Now I've plugged that into my graphing calculator here. You can do likewise if you want to kind of follow along. Looks like you got messed up, so let's try it again. Left parenthesis, 1 plus 1 divided by x, parentheses raised to the x power. And what we're going to do is we're going to look at what happens when you compound interest at different amounts of times per year. So to do that, I'm going to do a little table action. We can kind of think our way through the first 1 or 2. If you get 100% interest on your investment, so after 1 year they give you 100% of $1, that's $1. So you add that to the account. At the end of the year, you get $2. Okay, not too bad. But let's try and understand a little bit more about compounding and how that works. If you compound semi-annually, that is N is 2, twice a year, then if you invest January 1, you invest your $1, halfway through the year, July 1, they give you 50% of the interest. 50% of the interest would be 50 cents, so now your account has $1.50 in it. At the end of the year, December 31st, they give you the other half of the interest. What's 50% of $1.50? 75 cents. Add that to your account, now you got $2.25. So, okay, if you compound twice a year, you get a little bit more money back. Because what happened? You got interest on your interest, right? So that's nice. That's the effect of compounding. Now, after this, it gets a little hard to do this stuff kind of in your head. But we've got our calculator set up to help us do this stuff. So if you type in a 1, we see we get 2. 2, you get 2.25. And then 4 and 12 and so on. And you can see that you're getting all these numbers down here. Now something interesting is happening. you start making more and more money, but let's see, going from twice a year to 4 times a year, you get an extra 16 cents, and then an extra, let's see, did I get that right? No. Yeah, 20 cents. But when you go from 12 to 360, now 360 was what the banks consider daily interest. Last time I checked the calendar, there was 365 days a year, but this is literally what the banks do. All right, it doesn't really make a big difference, because if you jump up to 8,760 times per year, can you imagine how often that is? What would that be? More than 3 times a day. It's actually 24 times a day. Basically, it's hourly. If you're compounding interest hourly, then look what happens. You go from 360 to 8,760. You don't even get an extra half of a penny, do you? I mean, it makes the smallest of difference. So the jump from 360 to 365 would be pretty insignificant. In fact, you can play that game here. Put in 365. You can see it just really doesn't make a big difference. Anyways, with calculus, we can effectively put in infinity. And what would that mean? What that means is you're continuously compounding interest. It never stops. You get interest every second, of every hour, of the day, of the year. It just keeps on compounding continuously. And if somehow or another you're able to put in infinity, then you get the second most popular and most well-known constant in math, E. E is the base of the natural logarithm, which is what we'll see. But E is just this marvelous number, 2.71828, etc., etc., etc. It goes on forever. It never ends. It never repeats. And we're going to have to use E a lot. So one thing I want you to do is I want you to find E on your calculator. There's 2 places that you'll spot it. One is right above the division key. And I don't know why, but it took me an embarrassingly long time to discover that there was an E up here. I mean, I teach this stuff for a living, but if you hit the second key, then the division key, you get E. Yay. Now there's another place that you can find E, and it's right above the ln key. Right above the ln key, you see e to the x. So when I hit second and then e to the x, it says, all right, well, e to what power? Well, if you just want e, type in e to the first power. But maybe you want e squared, so see if you can't get e squared. And I'll pause here for a second to make sure that everyone's able to get e to some power for us, for all this. Okay, good. Now, one of the places that you're going to see E is in continuously compounded interest. So the formula for continuously compounded interest is this. It's A equals P. Now we're really starting out with this formula, but all this stuff really gets kind of subsumed, and we're going to replace it with E. PE to the RT. So when you're talking about continuously compounded interest, there's no more N. N is how many times a year interest is compounded, but if it's continuously, then that continuous part is built into the E here. So that's the formula we're going to use for continuously compounded interest. And let's practice with it a little bit. So we'll take a look at problem number 34. Okay, so we have $3,500 is going to be invested. So basically that's our P. At 6.25% per year. So R is 6.25%. And we want to compound that continuously. Find the value after, let's start with T equals 3 years. Okay. Armand? I'm not sure you grabbed the right one. So I'm going to plug that into the formula. A equals P e to the RT. There's one thing I need to take care of before I plug this in. Does anyone know what that is? R. The rate has to be expressed as a decimal, so it's going to be 0.0625. If you don't do that, you're going to get a hilariously large number. So let's take a look here. Filling this in, A equals 3,500, e to the 0.0625 times t, and t was 3. Let's see if we can't mimic that calculation on our calculator. So 3,500 second ln e to the 0.0625 times 3. Now you should get a reasonable number. Okay, 4221.8058. Where do I round this? What should I round this to for an answer when you hand in your exam? 0.8, 0.81. All right. So definitely has to be in the pennies digit, right? The hundredth digit. And so when you look at 0.8058, etc., that 5 means you're going to round up. So we'll round this to approximately $4,221.81. Yay. Okay, so how are we looking there? There's an old movie called Office Space. And the big premise, yeah, I see a couple of people like, yeah, I remember that one. And the big premise of the movie is that these guys who were working in the IT department of a big bank or financial institution decide that they're going to take that little bit of interest past the decimal point and just siphon it off of the accounts and into their account. And it's going to grow, and the bank won't know, and they'll be rich, and things don't go as planned, but I'll let you watch the movie after that. Okay, so let's try another one like that. Again, working with E. We'll do problem number 38, and we're going to do problem 38 because it asks us to work with our old formula for interest, and so you'll see that as a nice study in contrast. So which one would give a better investment or be a better investment? So you're going to invest your money for a year, 5 1/8%, compounded semi-annually. So that means n equals what? Semi-annually, n equals 2. Or 5% compounded continuously. Okay, well, let's see. Just to make this a little bit easier, let's think of investing $1,000. So we'll do let P equal $1,000, and our time is 1 year. Semi-annually means n equals 2, or continuously, U. And again, you're going to invest that $1,000 for 1 year. And our interest rate here is 5 1/8%. So it's going to be 5.125%, which we then got to turn into a decimal, 0.05125. Or over here, it was a nice simple 0.05, which is our 5%. So let's compare how much money is in each account at the end of 1 year. Which one do you think is going to be better? Continuously compounded at 5% or semi-annually at 5 1/8. You get more interest, but it's not compounded continuously. To be honest, I don't know myself. I'm leaning towards this one, but I really don't know. Okay, so the old formula for interest is this one. A equals P times 1 plus R over N to the NT. That's going to be 1,000 times 1 plus 0.05125 over 2. Right, that 2 comes from here. Raised to the 2 times 1 power. 1 because we got 1 year. And let's see how much money we're going to get at the end of our investment here. So 1,000, left parenthesis, 1 plus 0.05125 divided by 2 raised to the second power times 1, but times 1 is not going to change it. So I'm getting $1,051 and about 91 cents. Again, please make sure you round to the nearest penny. 1051.91. So there it is with the old formula. Let's take a look at what it would be if we compound continuously. If we compound continuously, then we're going to use this formula. A equals PE to the RT, which is going to be 1,000 e to the 0.05 times 1. And let's compare. Second ln, 0.05. I'll put the times 1 there, but you really don't need to put the times 1 in this particular one. Ooh, that was amazingly close. So, 1,051.27. So which one was better? Yes. Yeah, the 5 and the 8. All right. So it turned out that was better, although it's probably not worth a gallon of gas to drive a lot farther for this bank it is to this bank. It doesn't make a huge difference. The overall point here, though, is to get comfortable with the function e to the x. So how are we looking on that end? Looking okay there? Let's flip over our handout to the back. E to the x is just another exponential function. And I've got two exponential functions here. I've got e to the x and 2 to the x. Why don't you take a guess or try at deciding which one is which? Which one does it look like is which? Now, let's keep in mind something. E is approximately 2.718, 28, etc., etc., etc. So which one do you think is which? Which one's 2 to the x? The top one or the bottom one? Bottom one? Well, tell you what. Maybe we can do a little thought experiment. Einstein was famous for doing his thought experiments, right? Let's imagine plugging in x equal 1. So if I make a little table here, another one here, x and y, x and y. If I plug in x equal 1, what should I get here? Just e to the first power, right? What if I plug in a 1 over here? What should I get? 2. So, at x equal 1, well, there's 2, And that's a little bit higher than 2, right? Since this is 3 right here, then it's probably a pretty safe bet that this is the graph of y equals e to the x, and this is the graph of y equals 2 to the x. Both of these are exponential functions. Remember, there's 3 traits that exponential functions share. Do you remember what those were? What are the 3 things that they both share? All right, good. Gets close to the x-axis but never touches. So y equals 0 is an asymptote. All right, so it gets close to the x-axis, never touches it. Good. Someone else with something else. What else do these have in common? Yes?
As long as you do not have the up and down in the formula, it always has the y-axis intercept at 1.
Perfect. So as long as it's of this basic form, y equals b to the x, that is, it's not shifted, as Brian was saying, then, you know, the graph is going to pass through the point 0, 1. It's going to have that as an intercept. Passes through 0, 1. One other thing that really characterizes this, it grows quickly. Remember, we were talking about this when we were talking about Gangnam Style, the first video to have over 1 billion views. So it's a viral video. And it's a viral video because the number of views grows exponentially. It just explodes. It reaches a point where it just starts taking off. So grows quickly. All right, so we're going to work with these and translate them and flip them around and stuff like that. But the idea is that it's just going to be stuff like we were working with back in section 4.1, the exponential function. We shifted it around there. We're going to shift it around here. So let's look at a few graphs. We're going to do problems like 8, 10, 12, and 14. And I'm going to avail myself of some stuff here on Desmos, just for my absolute convenience. So let me see if I can't make that graph a little bit better. There we go. Okay, so here's the graph of your standard exponential, e to the x, and we've got this point going through there at 0, 1. Let me just put it there. Okay, so it's this graph that's going to get shifted around a little bit. And let's try and see and understand some of these things, understand some of the shifts. We'll start with problem number 8. Got to switch things over here. There we go. Problem number 8, we're going to look at the graph of y equals e to the negative x versus the graph of y equals e to the x. So the difference then is the negative here. What's that negative going to do to our graph? How is it going to change our graph? Yes, it's going to be reflected around the y-axis. So, good job. Let's take a look at that. Let me turn that graph on. And there, boom. It's exactly what it does. It flips that graph around the y-axis. So, let's take note of that. So, reflects around the y-axis. Okay, let's try another one. Problem number 10. Y equals 1 minus e to the x. Well, you might want to write it a little differently. We're still going to compare that to y equals e to the x. It's kind of our base function. But, to understand and see what's going on here, it might be more helpful to write that as negative e to the x plus 1. And there's two things that are happening to this graph that we have to understand. See if you can make some predictions about this graph based on those two things. How are these things going to change the graph of our function? And if you want, you can check these on your graphing calculators. Nothing wrong with that. You can pull up a graph and say, okay, well, here's e to the x, and then you can look at, you can type it in like this, 1 minus e to the x. Now, a good window to see that might be your standard window. Might want to zoom in a little bit, but you can get to the standard window really quick by hitting zoom 6. So there's your graph of e to the x. But let's make some predictions before I do the big reveal. Is this negative going to reflect around the y-axis? Good, around the x-axis. Thanks, John. So we're going to reflect around the x-axis. And then what's the plus 1 going to do? Yes. So it reflects around the x-axis. And then it got shifted up by 1. So two things. Now, personally, I'm not sure exactly why, but for me, it's a lot easier to envision those things when I rewrite the function the second way. It's harder for me to think of it here, but it's okay. We don't have to think of it that way. You can kind of see that if you look at your graph on your graphing calculator. So this graph has been reflected so that it opens down, and then I got shifted up by 1. And we'll take a look at it on Desmos. Manny, question? Okay. So, let's see here. Shut this one off. Negative e to the x, so that's been reflected down by 1, or just reflected down. And then if I shift it up by 1, bam, there you go. So you can see it's exactly what we expected. How are we looking on these graphs so far? Okay. Let's keep going with problem number 12. Zoom out a little bit. Problem number 12, kind of a combo. And try and figure out how this has been shifted, and then check with a neighbor. See if you agree. What's this going to look like? So for those of you viewing at home, we're going to do a little brief pause. So I don't have a pause button with this software. They've just kind of rigged it so I can work with it. It would cost like $800 for the manufacturer to configure it. So we do with what we can. All right. Chat it up. Talk to each other. Cam. Booyah needs a friend. Supposedly. If they cancel my trig class, I'll be in trouble. Would you be sorry? Yeah, I'll just put a cot in my office. All right. So, what's going on with this graph?
It'll flip around the x
yeah, so kind of a double flip. Flipped around the x-axis and flipped around the y-axis. What's that? You want to take a look at this one? Yeah? All right, let's take a look at this one. All right, it's a great idea. Let's see here. So problem number 12. Bam. There you go. So flipped around both the x and y axes. So you can see that it got flipped down. When you see that, what caused that was that part right there. But then when we put the negative there, we're going to take this graph in black and flip it around the y-axis. So, okay, much different looking graph, but it's still just a translated graph of the exponential. Let's do one last one. Problem number 14. This is the kind of stuff that I would want you to be able to answer on a test. How have these graphs been changed? So, let's see. Problem number 14 is y equals e to the x minus 3, and then plus 4, is it? Yeah, plus 4. All right, so maybe more of the traditional kind of changes to our graphs that we've made before. Two things are happening to our graph. See if you can't figure out what each of these are going to do to our graph. Okay. Contessa, what do you think the minus 3 is going to do to the graph? How is that going to change things? All right, shifted right 3. Do we agree with that? Let's find out. Let's take a look at it graphically speaking. So I'll shut this one off. And yeah, let's take a look at this one. So yeah, it's shifted to the right by 3. In fact, when you graph this for me on the exam, I want to see this point shifted to the right by 3 as well. So that's the point that I'm going to want to see on your graph depicted most accurately. All right, because for the most part, we're just going to be sketching a general shape, but I've made a big issue about this point being the y-intercept. That y-intercept is going to get shifted by 3. Now, let me just kind of show you that the whole graph has been shifted by 3 this way. This is where you go, ooh, ah, ready? Ooh, ah. So that distance is a consistent 3 from one curve to the next, no matter where you go. So it's been shifted to the right by 3. So what else happens to this graph? Yeah, up by 4. So again, let's try and take a look at what happens to the graph. We're going to take that graph there and shift it up by 4. Let's see. There we go. So it's going to be shifted up by 4. So this point here gets shifted to right by 3 and up by 4. So my new graph should pass through that point. Let's see that it does. Booyah. Nailed it. All right. So exactly right. All right. One more time. Ooh, ah. All right. Thank you. Are we okay with the shifting of these graphs? This is kind of a replay of some of the stuff we did in section 4.1, but it's exactly what I want you to know. It's a good skill to just be able to visualize, like, okay, yeah, I know what that graph's going to look like. Because sometimes when you input things into your calculator, you make a mistake. And if you get something that is way different than you expect, you can say, wait a minute, that doesn't look right. Because you know what you should be seeing. Okay, speaking of graphs, let's continue with graphs unless there's some more question about this one. All right, it's problem number 29, and I made a slight change in this to try and reflect, I think, today's conditions. So let's look at problem number 29. Ooh, you know what? There's probably one more thing I should mention about this last graph. Let me get rid of all this extra stuff here. And that one as well. So for this last graph on an exam, I'd probably also want you to tell me where the new horizontal asymptote is. So where's the new horizontal asymptote for this graph, the graph in red? Yeah, it's y equals 4. The original line here, the original horizontal asymptote is y equals 0, and we shifted our graph up 4. So the vertical shift is going to tell you where the new horizontal asymptote is. So y equals 4 is that horizontal asymptote. Okay, good. All right, let me get rid of these two graphs, and then we'll work on the next one, which is probably a little bit more accurate version of population growth as opposed to something that I may have used in your Math 1150 class. It looks like this. It's close to what's called a logistic model. And I just plotted this for x greater than 0. Why would I do that? Because we're looking forward into the future. It's not as if this graph doesn't exist for other values of x. It does. And we can see that if you wanted to see the whole graph. Let's start doing that. And let me adjust things this way as well. There. So there's the graph. What looks like it's happening with our population? This is world population. It's an estimate, but still world population. What looks like it's going on? What do you expect in the next 100 years or so? Is it increasing or decreasing? Increases, and then what happens? Levels off. At least I hope it levels off. I mean, there's already almost 8 billion people on this world. That's a lot. But you can kind of see that it levels off if you start putting in more and more values for x. So we can kind of watch, and it's plotting things, and it levels off somewhere, a little south of 13 billion maybe. Of course, this is going way, way out there. But you can see that these values aren't really changing that much, are they? They're kind of staying more or less the same here. So, okay. All right, but it's leveling off. So that's what the graph looks like. Why don't you see if you can't plug that equation into your graphing calculator? Oops, wrong one. This one. So I'll clear these out. Now, it kind of depends on you. If you've got a nice fancy graphing calculator and you can do a numerator and denominator, that's great. If you don't, just do this. 77.3 divided by parentheses 6.1 plus 5.9 e, so second and then the ln key, negative 0.02 x. And then you exit the exponent with the right arrow, and then a right parenthesis to finish things off. Now, quite often on an exam, you'll be working with, a graph already written for you or given to you. And so what you can do is kind of steal the dimensions of that graph to input for your window. So for us, we might want to do 0 to 600 on the y-axis or on the x-axis, and then 0 to 15. 0 to 15 on the y-axis. So let's set our window up like that. 0 to 600. Now, if I'm going to 600 on the y-axis or on the x-axis, I probably don't want to leave my scale as 1. Do I want to see 600 tick marks across the x-axis? I don't think so. it'd get pretty busy. So let's make this something a little bit bigger. Any suggestions? 100, yeah, that works good. That divides there evenly. 0 to 15, I don't know. I'd either do 3 or 5 for the scale here. Let's do 5. And hit the graph key. You should see a nice reflection of the graph that I have on your handout. Now here, let's see, let's look at the actual problem for the moment. So t equals 0 is the year 2000. And I asked us to find the population in the year 2200. So what should I put into my model to find out how many people are going to be here in the year 2200? What would the value of t be for this, or this for that matter? I'm getting a wall of silence. You're making me look back. Come on. Well, what's the difference between 2000 and 2200? 200. So this is t equals 200 years past 2000. So to get this, you plug in 200. Now we've already got our function in our calculators. So what I'm going to do is hit the second key, then the table key, and just make my calculator do all this. I'll delete all this stuff here and type in a 200. I get 12.452. Okay, that's fine. What do I do to get the population in the year 2300? Yeah, 300. 12.64. Okay. Now, if you're curious as to where's this all going, where's the population topping out at, then let's put in a big number. Let's put in like 10,000. Actually, that's 100,000. Let's try 10,000. Is there a big difference between 300 and 10,000? No, it's kind of leveling off, right? Now, if you want to see more digits here, come up with the cursor and put it on that number, and you'll see all the digits that you want right down below. So it's starting to level off at around 12.67. Of course, that's in units of billions, which is really, really big, but levels off. There's lots of models that involve E. Skydiving, your terminal velocity. And I always thought that was kind of like a poor choice of words when you're talking about skydiving, right? Terminal velocity. There's a bad implication there. But the terminal velocity involves E. In fact, something in the news lately would involve E. What's the big thing in the news? Coronavirus, right? So the spread of a virus can be modeled with functions based on E. So, okay. Let me just fill in a couple of these for problem 29. So part A, B, and C. So T equals 200. The population was 12.452. For T equals 300, population was 12.62, or 642. Sketch the graph. Well, we've already done that. That's on our handout. And then according to the model, what size of the population approach as time goes on? Well, it looks like it's approaching 12.67. What's happening here, and let's see if we can't think about this way. Think about the function e to the negative 0.02x. Well, is that going to be a function that's growing or is it decaying? Which one do you think it's going to do? E to the negative 0.02x. Is it going to grow or decay? It should decay, right? Because it's been reflected around the y-axis. So it's going to decay slowly. So eventually this term is going to be 0. And the overall population is going to get closer and closer to 77.3 divided by this. Because if this turns into 0, you're just going to be divided by 6.1. So about 12.672, which is what we saw from our table. We get the same thing here. So 12.672 for C. Nice. Okay. Should we do one more? Kind of like that, maybe problem number 28, or are you comfortable with population problems? Okay. Since no one's really clamoring for some more work on that, let me give you some homework. For homework, try 5 through 13, 23 through 27, 33, and 35. And 35 has a little box on it in my notes. I don't know what that means, though. This is for section 4.2, yes. Cool. Thanks.